Hello my dear students, welcome back to NEET World. So today we will be continuing our discussion for IPE exam for both Telangana and AP students. Okay, so here in this session I will be covering intermediate second year 4 marks question from solid state, and I hope you are all aware that definitely there will be one question from solid state in your final exam, right? And that will be for 4 marks. Okay, so we will discuss that very clearly. Okay, right. Now this is our C60 material designed to score 60 out of 60. It will be useful for both AP and Telangana students who are preparing for IPE exams. Okay, now you can access this material for free of cost from our NEET World app. Okay, just go to Play Store and download NEET World app. Okay, so after downloading it, just log in using your mobile number. Okay, then just say your class and your group in the chat box, then our team will guide you how to access this material for free of cost. Okay, I hope you got this clarity that how can you access this material and make your preparation more effective. Okay, right. Now let's continue our discussion on solid state chemistry. Yeah, so other topics I have already discussed. Okay, and few more topics to be discussed, then it will be completed. Okay, right. Yeah, so look at this when it comes to solid state. So here we can expect, see, we can guess 3 to 4 questions. I mean, we can choose 3 to 4 questions. Out of that 4 questions or 5 questions, we can definitely get one 4 marks question in your final exam. And most repeated question is this Bragg's equation question only. Okay, so solid state 4 marks means most of the times we can get a question on this only, like derive Bragg's equation. Okay, so this is the expected question in your final exam. Okay, let's understand this question very effectively so that it will be useful for both your IPE preparation as well as your board exam, I mean as well as your EAP set exam also. Okay, so just follow me. Yeah guys, and you know this solid state chemistry is not there in your NEET and JEE exams. Okay, so most of the students have studied this properly previous. Okay, so now you need to focus on this to get your 4 marks from this chapter or to score 60 out of 60 in your final exam. Okay, right. Yeah, let me check the voice is clear. Mostly. Yes, voice is clear. Mostly, repeat. Yeah, so let's continue our discussion on this. Yeah, see, if there is any discrepancy or disturbance in the class discussion, you please mention in the chat box so that we will look into it. See, the question says, see, what is the use of Bragg's equation and what exactly Bragg's equation? I will tell you, just listen here. See, we know the chapter name and solid state. So let us take some solid crystals. Okay, so if you consider any solid crystal, okay, so now what happens in these solid crystals? Atoms are arranged in a regular fashion, in a fixed manner, right now. So it means, see, if you take a crystal lattice, what do we mean by crystal lattice? A crystal is made up of some atoms, right now. So that atoms are oriented in a regular, like a fixed way of arrangement, right? So let us say this is a plane, this is a second plane, this is the third plane of a crystal lattice. Okay, now in this plane, see, atoms are arranged in a fixed manner, like a regular pattern, right? Okay, so now what happens is we have first plane, second plane, third plane, like this. So using Bragg's equation, we can able to calculate what is the interplanar distance, what is the distance between two planes in the crystal structures of this solid crystals. Okay, so what is the use of Bragg's equation? we can able to calculate the interplanar distance between the two planes. We can use we can calculate using our Bragg's equation. This is the first application you can remember. Okay, now I will tell you how do we do and how do we calculate all these things. It's very easy, just follow my direction, because most of the time this is the question asked in the exam. Most of the students are not aware how to attempt it. Okay, so just draw the planes and indicate the atoms like this. Okay, so now what we do is consider the distance. Small d is the distance between the two planes. Okay, small d is the distance between the two planes, that is interplanar distance we can say. Okay, so now you just take the x-rays. What we are taking? X-rays. Now you are taking an x-ray. Okay, so you are in
5%. So this is the percentage change in expenditure.
Okay, so in the similar way you are taking one more x-ray, that is second ray. So that is incident on the, that will be incident on the second ray, second plane. Second ray is incidenting on the second ray. Okay, like this. And if you observe, I have drawn the lines like this. I mean, I draw the x-rays in this manner like this. Okay, so now what do we mean by a wave? Wave means like this you need to indicate. Okay, this is a full wave. Okay, this is a full cycle. You can say it's a full wave. Okay, so now if you see, this upper side is there. Now this is called crust and this is called a trough. Okay, so now if you see, the crust of the second wave, crust of the first wave are in same plane now, so it will give a constructive interference, you can remember. Okay, this again you will study in physics also. So this is called constructive interference. See, the trough, this down one is there now, this one and this one, these are called trough. The trough are also in the same plane, so it means when they combine we will get a constructive interference. Crust, trough should be added, so that we will get a resultant amplitude with a constructive interference. Okay, so this concept you need to remember. Okay, this is small things to be discussed here. Okay, so you got to know there is a first ray and second ray, we are incidenting on these planes. Okay, right, first ray on the first plane, second ray incident on the second plane. Okay, these are the lines I am using to indicate the x-rays. Okay, so now if you see, this is the theta with the incidenting of the first line we are seeing. Okay, so the same angle will be seen here also. The same angle will be seen here also, because here theta, here also theta. Okay, remember this. Now what I am saying is, if you observe, the first ray is traveled from if you observe, the first ray is traveled from here to here only. But if you observe, second ray is traveled from here to here and an extra distance of this much. This is an extra distance right now. So this side also if you see, is coming and incidenting here and it is getting bounced back to the other side like this, reflected to the other side. In the similar way, the second ray also getting and after incidenting here, it is bouncing back like
by 3.
Okay, like this. Okay, now
4, that is 25.
Second ray is traveling some extra distance compared.
Decrease the consumption by 20.
Okay, so this is the part of extra distance traveled by the second ray like this. This is the part of
next question.
Extra distance traveled by the second ray compared with the first ray right now. So now you just add these points. See, from here to here equal distance, from here to here equal distance. But this is an extra distance traveled by the second ray right now. So let us highlight them. This as the dot A and this as B, D, here B, here C. Like this, we have taken 4 points here. So now what is the extra distance traveled by second ray? The extra distance traveled by second ray is, you can say the extra distance traveled by the extra distance traveled by second ray is equals to dB plus or BD plus BC. Right now, this one plus this one. See, BD or dB plus BC. This is the extra distance traveled by second ray, right? Yeah, you just it. Okay. Now from the above diagram, the extra distance traveled by the second is how much? dB plus BC. That is what you need to simply mention in the exam. Okay, then next. Now if we observe, we have something like this. If you observe, this is how we have. So this is A we are saying, this is B we are saying, CD. And what I told you, the distance between the two planes is called interplanar distance. Now, yes, I am drawing this as an interplanar distance. What is this violet color line indicates? It's a interplanar distance between the two planes. Okay, that is indicated with a capital D. Okay, so now if you observe, see, this is a line we have drawn like a normal line here. This is how much? 90 degrees. Okay, whereas this is the upper one, here it is theta. Here also theta. Okay, both thetas are same. Okay, so now what we can write? Sin theta is equals to sin this theta. Sin theta is equals to opposite side by hypotenuse. Right now, opposite side by hypotenuse. So what is the opposite side for this theta? That is BD. Right? What is this? DB or BD. Okay, see. To this theta, what is the opposite side? This one only, no? So that is nothing but BD. So to this theta, here we have indicated theta, no? To that opposite side is DB or BD only, no? Right. So that you can write opposite side is BD. Yes, we have written. So what is the hypotenuse? See, to this 90 degrees, opposite side is hypotenuse, you can say. To
Expenditure.
opposite
Now they are given what are the values? Price.
hypotenuse, I am saying how to identify hypotenuse. Okay, opposite side means you have to take with respect to theta. With respect to theta, this is theta. This is BD is a opposite side. And what do we what we can consider hypotenuse? This one, this line. So what is that? It is AD. Okay, so sin theta equals to BD by AD, you can say. Okay, so now what is this AD value? This is interplanar distance. Now how much it is? D. So AD value is given as D. So BD is equals to BD by AD. AD value is how much we got? D. So I can write BD is equals to, I can send this D here, it becomes D sin theta, right? So D sin theta. Okay, now what I told you, we got from this triangle, this half triangle, we got BD is equals to D sin theta. Actually, why we are finding this BD? Because we got to know this is the extra distance travelled. This BD and CB is the extra distance travelled by the secondary. That extra distance we are calculating now. Okay, so BD is equals to D sin theta. And similarly, BC also, from this triangle, again you will get sin theta is equals to hypotenuse by hypotenuse. So opposite side is what? Opposite side is this one. So you can say opposite side is BC. Okay, this is you need to take these values from there now. So this is D, this is B. So opposite side is how much? This one. To this theta, this is the opposite side now, that is BC. Okay, and hypotenuse here is AD. Okay, that's it. Not AD. That's it. AD. Okay, so now what happens from this? We got a DB. That
What?
And BC also gives you same D sin theta only. Okay, you got D sin theta only. So you got D.
3 9s are this is
BC values you got, not D.
0.5.
You got how much it is? This is D sin theta. This is, both of them are D sin thetas only. Just add them, you will get 2D sin theta. So what is the extra distance travelled? That is 2D sin theta. Okay, and you know guys, what I told you the concept called constructive interference. Now two waves should be in the same plane, same phase, that overlapping gives you constructive interference, like that. Okay, trough, crust should be in the same phase, that overlapping gives you a constructive interference, I told you. Okay, so for that purpose, it means for having that condition for a constructive interference, this extra distance, this path length, we have now dB plus BC is there now. So this should be equals to n lambda. So what is this? Lambda indicates, lambda is the wavelength. What is that? Wavelength. And n represents the number of waves. Okay, so you can see here we are seeing now, like this wave is coming like this, we are saying now. So that is, lambda indicates wavelength. So this one, this is a wave, the length of this wave, lambda, this wavelength we can say. So number of waves, n, it is indicated. So now BC. So what is this extra distance I told you? This is sin theta, D sin theta, this is also D sin theta, right? So this is equals to n lambda. So you can simply write 2D sin theta equals to n lambda. Yes, this is your final Bragg's equation. That's it. So this is what you need to write in your final exam. Okay, hope the discussion is clear. Guys, if the discussion is clear, just click on the like button so that I consider you are clear with the discussion. Yeah, let's move forward. See, everything, you no need of worrying in about anything. See, everything that required for you I have mentioned in this note. Yes. Either you can take screenshots for this answer, or you directly download our material from our NEET World app. Okay, right. So everything is clear. You just go through these lines, whatever I have explained, mentioned here. Yeah, you just mention as it is in your final exam to get full out of full marks. Okay, right. So let's move forward. Yeah, so now the second question from the same solid state chapter we can expect is Schottky defect and Frankel defects. Explain Schottky and Frankel defect from here. Okay, just listen to me, you will get the clarity. Okay, it's very easy. Schottky. Okay, so what it is saying? So Schottky defect or Schottky defect, some people will Schottky also. I can say it as Schottky defect. Okay, it's a point defect. What is it? It's a point defect. Okay, so this defect arises when equal number of cations and anions are missing from their lattice. Okay, if you consider lattice, what do we mean by lattice? So it is a arrangement of atoms, like for example sodium chloride crystal if I consider. So now we have sodium cation and chloride anion, right now. So they will be arranged in a proper way, like AB, like this, a cation and anion, like this. It will be properly oriented in this structure, like in the lattice formation. Okay, right. So now what happens is, this defect, these are both of them are Frankel and Schottky, these are defects. Okay, so this Schottky defect will be erased. Okay, this will be developed or this will be seen when same number of cations, same number of anions are missing from this crystal lattice. If same number of cations and anions are missing, what happens? There will get a holes. See, from here I am removing something. So what happens? In that space we will be creating hole, no? Yes, holes will be created. Okay, our interstitial sites or holes will be, so you can say simply as holes will be created. So just read, this defect arises when equal number of cations and anions are missing from their normal lattice. Okay, so the crystal remains electrically neutral. So these points are also important for your EAP set exams also, along with your IPE. See, if the same number of cations and anions, same number of plus charges and minus charges are removed, now what happens? It maintains electrical neutrality only, no? Right. See, so
Initial, final. Initial
same number of missing positive and negative charges are seen. Right now, the defect, this defect is common in highly ionic compounds, in which it is
Multiply.
common in highly ionic compounds. It is common. That ionic compounds, that ions should have similar sizes of cation and anion and a high coordination number. They should have high coordination number.
Clear.
Okay. So the best example here is cesium chloride. You can remember cesium chloride, large size cation, no? So you can remember in that way. Okay, the density of crystal decreases due to missing of ion. See, what do we mean by density? This is mass by volume, now. So in the same volume we are removing some particles. See, we are removing a cation and anion. What happens to mass of that substance? That crystal decreases now. So density also decreases. So you can remember, due to Schottky defect, density of the crystal decreases. Okay, why it is decreases? Because same cations and anions are completely missing out of that lattice. Right now it is not present in the lattice now, they are coming out of it. Okay, and they are creating holes. So due to that, being same volume but mass, that is amount of substance or the atoms are removed now, so that's why density decreases. Just remember in that way. Okay, right. So this is how you can represent it in a diagrammatic way also, the final exam. Okay, that's it. Write the examples and represent this one. Okay, the next here we have Frankel defect. Schottky defect means both cation and anions comes out of the crystal. But in Frankel defect, what it will do is, a ion will occupy some interstitial site instead of its original site. Okay, I will tell you, just follow me. See, Frankel defect is also a point defect. It arises when an ion, usually cation. So what it will do? It leaves its position. See, if this is a crystal lattice, for example, you are writing like crystal lattice like A, B, like this we have arrangement A, A, B, B. Like this we have equal number of cations, anions initially consider. Okay. Now what I am saying is some of these cations, let us say this A is a cation. So this cation, instead of occupying its original site like this, instead it won't be here, somewhere in between, some random position, like somewhere other site will be occupied. So this is called interstitial site. Now you can assume this. See, AB is a crystal lattice. See, this is the position of a cation. But do we have a cation here? That A is missing here. See, B is there. Between A it is missing now. So that A, instead of having its original normal site, it is went somewhere over here. See, here we have a cation. So due to this type of defects, the concept is called, the defect arises due to this type of phenomena. We can say it as a Frankel defect. Okay. So now what happens again? Will this crystal lattice remains neutral, or any charges are developed? No, it will remains neutral only now. See, ions are not removed from this lattice. They will be in the lattice only, but not in the original site, but somewhere on the some other place, interstitial site. Some ions will misses from their original sites, occupy some lattice like interstitial sites right now. So overall molecule will be, overall crystal will be neutral, and there is no change in the density also, because atoms are not removed out of the crystal. It is being in that only, but some other position maybe. Okay, so that's why density also remains the same before and after the defect also. Okay, now read this. The crystal remains electrically neutral. Yes, crystal remains electrically neutral as number of cations and anions are same here. Okay, because no anions are missing, they are only displaced from their original position, they are displaced to some interstitial position. This defect occurs in ionic compounds with a large difference in size between cation and anion with a low coordination number. So they should have a low coordination number. Okay, so the density of this crystal remains unchanged since no ions are lost from their sites, right? So now what are the examples here? We have Ag
For one is
silver iodide,
marks you will pass.
sulfide are the examples for this Frankel defect forming crystals. Okay, hope the discussion is clear. Right. Let us move forward. Yeah, the next question here we have is describe two main types of semiconductors. Okay, yeah, so that is the last question, I think so. Yeah, one more question maximum. Yeah, only that is the last question. These are the three questions you should focus from solid state first. Okay, right. And if you have time, yes, you can go through other questions also, but first finish these three questions from this chapter. Okay, so the third question here is describe two types of semiconductors and contrast their conduction mechanism. Okay, we need to describe what are these semiconductors and we need to describe them properly. Okay, and we need to compare them each other. Okay, so look at this. Semiconductors are solids whose conductivity lies between conductors like metals and insulators like glass. See, we know conductors means which have capacity to conduct electricity, to allow the passage of electrons or electricity through them. Right now, those are conductors. Now, insulator means they won't allow the passage of electricity through them. Right now, what are the examples for insulator here? We have glass and there is some plastic items considered to be insulators. Right now, so now here metals and electrolytes are the good conductors of electricity. Right now. So now when it comes to semiconductors, it has intermediate properties between these conductors and the insulator. Okay, right. We'll see that in the diagram. Let us look into it. There are two types of semiconductors and the behavior of the semiconductors are explained using energy band, like conduction band, this thing, valency bond, this thing will be used here. Okay, right. So now here you see intrinsic semiconductors. What is this? Intrinsic intrinsic semiconductors.
Where 35% to
Conductors without any impurities.
okay. What is the total?
Semiconductors. These are the two types of conductors we have. First one, intrinsic semiconductors. There is no there is no impurity here. See, these are pure conductors without any impurity. Okay. Then next, the energy gap between valency bond and conduction band is very small. See here, if you observe valency bond, conduction bond is there. So for insulator there will be a large gap. Okay, so we can say this is a large band gap. So if there is a large band gap, therefore electron transfer, electron movement will be very difficult. There is no passage of electricity, we can say. So it is considered to be an insulator. Whereas here in gap, this band gap is very moderate. When it comes to conductors, there is no gap or a very small gap or no gap will be observed, and it is free to conduct. Okay, so now you can, the energy gap between valency bond and conduction band is small. Okay, so now the when temperature increases, some electrons jumps from valency band to conduction band. So when we increase the temperature, what happens? Electrons from valency band to conduction bond, they will jump. Okay, that's how electricity will be passing. Okay, and that's how they will act as a conductors. The movement of electrons in conduction band and movement of holes in valency bond provides electrical conductivity. So now what happens when an electron is jumping from valency band to conduction band? Here it will create an hole, here it will be having an electron. So due to the movement of this electron in the conduction band and holes in the valency bond, we can expect the conductivity. Okay, so the movement of electrons in conduction band, movement of holes in the valency bond produces electrical conductivity. So the conductivity increases with a rise in temperature. So conductivity increases with a rise in temperature for intrinsic semiconductors. Examples here, silicon and germanium are the example provided here. Okay, now let us see for extrinsic semiconductors. So in extrinsic semiconductors, the conductivity is due to presence of some impurities. Okay, so to that material we are adding some impurities. Due to the presence of that impurities, it will be showing the semiconductor properties. See, they are obtained by adding small quantity. It means extrinsic semiconductors are obtained by adding small quantity of suitable impurities, okay, to the pure semiconductor. Okay, so this process is called doping. Okay, so to the pure semiconductor we are adding some quantity of impurity. So due to that we are getting our extrinsic semiconductor right now. So process of adding an impurity to this pure substance can be considered to be doping. What is that word? Doping. Okay, so depending upon the type of impurity we are adding, extrinsic semiconductors are again classified into two types. One is P type, other one is N type. P type and N type semiconductors. See here, N type, these are formed, N type are formed by adding group 15. Just remember group 15. Group 15 is nothing but nitrogen family, no? So nitrogen, N. So you can remember it as N type semiconductors. Okay, just for remembering purpose I am giving you this tricky way, that's it. Okay, so these N type semiconductors are formed by adding group 15 elements. What are the group 15 elements you can add here? So it can be phosphorus, arsenic, antimony to the silicon or the germanium. See, you just take group 14 elements to this group 14. If you are adding group 15 elements, you can say this is N type. To this group 14 elements, if you are adding group 13 elements as an impurity, then you can say this is a P type semiconductors. If it is group 15, you can say P type. If you are adding group 13, you can say P type. If you are adding group 15, you can say N type. Okay, to which group we are adding which group elements? To the 14th group elements. Okay, silicon and germanium belongs to 14th group, right? So to this, if you are adding phosphorus, arsenic, antimony, so in group 14 we have valency electrons as 4, but in group 15 we have 5 valency electrons, right? So due to one extra electrons, when we are adding this group 15 element, we will be, due to extra electron, that extra electron act as a charge carrier. So therefore it is called as N type semiconductor, okay, or N type semiconductor or extrinsic conductor. So the next, when we are adding group 13th to the group 14, see in 14th group we have 4 valence electron, in group 13, like what is this boron family, boron, aluminium, gallium, these things. So it have only 3 valency electrons. Since we are adding 3 electrons to this, it will create a hole. What it will create? A hole is created. So look at here, formed by adding group 13 elements to the silicon or germanium, a hole, electron vacancy is created. That will act as a charge carrier. Here electron in n-type semiconductor, electron act as a charge carrier. In p-type semiconductor, a hole act as a charge carrier. So due to this reason, they will be considered to be extrinsic semiconductors. I hope the complete discussion of these 3 questions are clear without having any confusion, right? So if there is no confusion, just click on the like button. If you are new to this channel, click on the follow button. And if you have any confusion, feel free to express in the chat box. Someone, sir, solid state nundi only Bragg's equation vastadi kada. Yes, mostly Bragg's equation. That's why I told you, you need to focus on Bragg's equation first. But along with that, you can focus these 2 more questions. That's it. Okay? Yeah. So this is about the session. Yeah. So you can represent this n-type and p-type semiconductors in a diagrammatical way like this. Okay, that's it. This is more than enough. Okay? Yeah. I hope the complete session is useful and there is no questions to be discussed from this chapter. These are more than enough. And if you wanted to cover few more chapters, I mean in the upcoming sessions we will be covering few more chapters, and if you have any doubts, feel free to express. I will cover them in the upcoming sessions. Okay? Yes, if you have time, yes, you can check for the other questions also, but these are more than enough. So thank you for watching. Stay connected with our NEET World YouTube channel. Thank you.